Hello, everybody. Congrats on Physics 103. Congrats on completing week 2 of our busy semester. Unlike last week, things are going to be a lot more concise moving forward. And for this week's compressed worksheet, it's going to be two parts, two lessons. First part is work and power. And so what we have here is some sample free body diagram where we have some applied force that is not perfectly to the right or up, but to it is 60 degrees above the positive x-axis direction. We also have our force of friction, which is 40 newtons pulling directly to the left. Force of gravity and the normal force are both 29 newtons. As far as our applied force, it has a magnitude of 80 newtons. Now, what we care about is, for this problem, all we really care about is the applied force's x components. We're just seeing our object move a distance of 4.5 meters to the right. So because that's the only direction of motion, we only care about the x component of our applied force. And when it comes to power, the time duration is going to be 2.1 seconds. So first things first, we need the x component of our applied force since it's not directly to the right. Well, Fpx is going to be the applied force times cosine of 60 degrees, 60 degrees being what we have here. Now the applied force was 80 newtons, and cosine of 60 degrees, if you plug that into your calculator and it's set to degrees and not radians, you should see that that equals 1/2 or 0.5. So 80 newtons times 1/2 is 40 newtons for our applied force's x component, or the component in the direction of motion. Now, if we're just going to do this with the net force method, instead of calculating a work for every individual force, what we're going to use is just the net force is the applied force's x component minus the force of friction, 40 minus 15 newtons, which gets us to 25 newtons. Therefore, our net work would be the net force times the distance vector times cosine of 0 degrees. Not 60 degrees, but since our x component of force and the force of friction, overall that's just going to be an x component force. That force will be directly to the right. The distance vector is directly to the right. So if they're parallel and pointed in the same direction, then the angle between them is 0. So don't let that 60 degrees trick you up here. Essentially, if you use 60 to calculate this, then you're no longer needing that angle. But the net force, 45 minus 15, that would be 25 newtons. The distance vector, we're told the object travels 4.5 meters, so that would be our distance vector. And as far as cosine of 0 degrees, that's the same thing as positive 1. So what we end up getting is 112.5 joules of energy. Positive, that just means that that's energy that's being used to push this object, so energy being pushed into the system to move it. Naturally, power, that will just be the net work divided by our time of this transition. Well, the work we calculated was 112.5 joules. We're told that the change in time for this entire transition is 2.1 seconds. So 112.5 joules divided by 2.1 seconds gets us 53.6 watts of power. And that will be part 1 of your worksheet. Now, for the next part, this is going to be torque. So instead of thinking of translational motion along some axis, this will be rotational motion along some rotational axis. What we see here in our chart, we have applied force number 1 of 40 over square root of 2 newtons, applied force 2, which is a magnitude of 10 newtons. Of those two forces, applied force 1 is at an angle of 60 degrees, and applied force 2 is at an angle of 150 degrees relative to our horizontal rotating bar. We have two hanging weights, weight A that we do not know its weight of, and then weight B, which is 20 newtons. The bar itself has a weight of 5 newtons, so its force of gravity will be in the center of our bar. The bar has the dimensions 25 plus 5 plus 10, so a total of 40 meters. Therefore, the force of gravity of our bar will be directly halfway, which is going to be 20 meters from either end if the entire length is 40 meters. So that's why I have FB, or force of the bar, 20 meters away from the end. This X here is our point of rotation. So we care about the distance between all of our forces to this point. Now let's look at the torque of all of our forces. Well, TB, or the torque of our bar's force of gravity, we are already told that it is 5 newtons. So we plug that here. As far as the distance vector, well, we have our point of rotation here. If this force is at the halfway point, or 20 meters away, 20 meters away from the edge, and this entire arrow is 25 meters, then the difference is going to be 5 meters. So this force is 5 meters away from our point of rotation, hence why we have that here. And then sine of 90 degrees, well, these are because if our bar is horizontal and our force of gravity is vertical, then the angle between the distance vector and the force vector is 90 degrees. Lastly, the positive sign is just to take account of the fact that this force, if we stretch it and bend it toward our point of rotation, that would be a counterclockwise torque. So we're going to make that positive. Positive times 5 times 5 times sine of 90 degrees should come out to positive 25 Newton meters. Unlike with work, where these units become joules, for torque, we leave them as Newton meters. Now, torque of our weight. Well, this is going to be our known weight. We know that this weight right here has a weight of 20 newtons. Hence the 20 newtons. We can already see from this arrow in our schematic that this force is 5 meters away from our point of rotation. Hence why there's 5 there. And now this is a vertical force. This is a horizontal bar, so the angle is 90 degrees. And the reason why I have a negative sign here is because the force of gravity for this weight is straight down, but as we start bending it toward our point of rotation, that is going to be clockwise rotation. And clockwise rotation is negative in the torque vector. So negative times 20 times 5 times sine of 90 degrees should come out to negative 100 Newton meters. Next we have is the torque of our first applied force, FP1. Its magnitude is 40 over square root of 2. We're already told from our schematic that this force is 10 meters away from our point of rotation, hence the 10. Why we're using 60 degrees is because that's the angle we're given. Now, if we were given its complementary angle, the larger angle, you could use that value instead, because sine of complementary angles equal the same thing. So sine of 60 degrees, sine of 120 degrees, it would equal the same thing. But we're given the 60, so that's why we'll plug that in, 60, sine of 60 degrees. Now, since we're using sine, we're thinking of the y component of our forces. This force is at an angle, but its y component is up. So if we touch the bar, move up, and start bending toward that x, toward that point of rotation, this is going to be clockwise rotation. hence the negative sign. Bringing all these together, you should get about negative 244.9 Newton meters for the first applied force. And for our last applied force, FP2, its magnitude is 10 newtons. As far as the distance vector, well, we're told that our applied force 2 is at this point. We're told this distance is 10 meters and this distance is 5 meters. So the total distance away from our point of rotation is 15. As far as the angle, well, we're given 150 degrees. Again, if you were given the smaller angle of 30 degrees, you could use either because sine of complementary angles will give the same thing. So sine of this larger angle or sine of the smaller angle, it will equal the same thing. So we're given 150. So let's plug in 150. And the positive sign, if we're thinking of the y component, this arrow to the right and up, the y component is up. So if we touch our bar, move up, and then bend toward our point of rotation, this is going to be counterclockwise rotation, hence the positive sign. Thus, positive times 10 times 15 times sine of 150 degrees. If you plug this into your calculator, you should get positive 75 Newton meters. These are all of our known torques. So if we add all those together, we get negative 244.9 Newton meters. Now, this is not our net torque because our net torque has to take into account the torque of object A. So our net torque equals the torque of object A minus 244.9 Newton meters. The reason why torque A is positive, or we're not including a negative sign in front of it, is because torque A is going to be from a force of gravity. Gravity is going to be straight down, and as we bend it toward our point of rotation, this force from object A would cause counterclockwise rotation. Hence, positive torque of A minus 244.9. Reading our problem, this is an X represents the pivot point of our bar. In order for the bar to be at static equilibrium, that means that the net torque equals 0. What must the weight of mass A be? Note that the weight of the bar is 5 newtons. The key here is this object is at static equilibrium, rotational static equilibrium, so it should not rotate at all. That means that the net torque equals 0. So we have the torque of object A, which we know is a positive torque, and that is being subtracted by the remaining amount that we have. Or I should say, we're adding to it the additional torque of everything else. The additional torque was negative, hence torque A minus 244.9. Adding this to the other side, torque of object A has to be 244.9 Newton meters. Now, torque of object A, that is the force of object A times its distance from the pivot point times sine of the angle between these two vectors. As far as the distance vector, well, we're already told that this object is 25 meters from our pivot point, hence the 25. This distance is horizontal. Object A has a force of gravity that is vertical, so that is an angle of 90 degrees, hence the 90 degrees. Now this mass and 10, well, the thing is, force of object A, that can be broken down into a mass times 10. 10 being the acceleration due to gravity. Let's see. There we go. Uh, I noticed a typo that I should have called out. This side right here is if we are trying to solve for the mass of object A. So breaking that force into its mass times the acceleration due to gravity, which your worksheet labels as 10 meters per second squared. That would therefore become the mass times 10 times 25 times sine 90 degrees. That would be the mass times 250 meters. Let's see. Per seconds squared kilograms. And then dividing 250 to the other side, the mass would be 0.9796 kilograms. However, apologies for the typo. This problem asks what must the weight be? And weight and mass are two different things. So instead of solving for the mass, what you would solve for is the force, Fa. So torque of A equals its force times the distance times sine of 90 degrees. Torque of A was already determined to be 244.9 Newton meters. And the force of A multiplied by the distance, 25 meters, times 1, which is what sine of 90 equals. This was a positive torque, which is why we don't have a negative sign here. Dividing 25 to the other side, we get our actual answer, which is the force of object A, its weight has to be 9.796 newtons. So for this particular problem, you were asked for the weight. This would be the answer. If you instead were asked for the mass, then that would involve this extra step here. So once again, just a heads up. The worksheet that you have asks for the mass of weight A. So this got switched. Your actual worksheet for class is asking you to solve for the mass. Now, if you were asked to solve for just the force, the weight of object A, then you wouldn't need to go so far. You would just follow this step here. In any case, for your actual worksheet, you just have to do this sign. This is just a little extra if you are ever asked to solve for the force instead. In any case, I wish you all the best on another successful week. And, of course, peace.